Now we will have Rafa, who will continue talking about this topic and hopefully provide a different perspective. So Rafa, it's all yours.
Thanks, Regina, and thanks, Gian. I had seen an anonymous paper online with this content, and I was very excited to see this in a talk. I'm going to discuss, a little bit more on sort of on the two sides of what Gian just described, right? Like, I'm going to talk about, how 3D information, and particularly the fact that molecules are many 3D structures at the same time, could help structure property relationships, right? Property prediction, and how we made a data set to help people answer them questions too. So at a high level, and maybe tying with what I started with earlier, structure property prediction, right? We've been doing this as cheminformatics for a long time. Is, as far as machine learning is concerned, to a large degree, a representation learning problem, where the key part is processing, the raw molecular representation into some, low-dimensional vector that we can then map to properties. And that's something that has a long history, like I said, and, Morgan fingerprints that came up, a couple of talks back from Maxime, and random forests are a surprisingly hard baseline to beat. So it's always good to keep those, in your reference table. And I think by now you've probably seen, even if you weren't aware of them, that graph-convolutional architectures work really, really well on molecules for a number of reasons, right? Like they're end-to-end learnable, so they learn the representation that works best for the task. They're natively permutation invariant, which is really important, right? Whenever somebody writes a molecule as a string, somewhere someone made a decision of how to permute the hundreds of characters that make that molecule. So it's a single point in a very high dimensional combinatorial space of arrangements of characters, which is a painful thing to deal with in representation learning. Like I said, they can be customized graph neural networks, but they can also be pre-trained by somebody else, and then you pop by and you only use the embedding that they learn, the molecular representation, but maybe you don't need to move all the weights that make up the representation. But they're typically data hungry, right? We're talking tens of thousands of points to start moving the needle. And they act on graphs, but actually molecules, are not exactly graphs, right? Molecules can be captured completely as a stereochemical formula. The stereochemical formula is a graph with a special type of edge annotations to represent chirality and ZE isomerism. So a graph with these special annotations on the edges and nodes becomes a stereochemical formula that explains everything a molecule is, right? With that graph, a chemist, knows what's in the bottle, knows what they're making, and that's input enough to predict the properties of the whole molecule. But at the same time, the molecule in reality is an ensemble of atoms that exist in three-dimensional space, right? And they act as a three-dimensional entity. When they bind a protein, it's a three-dimensional version of the graph, one specific three-dimensional version that binds the protein. So when we're doing graph to property regression, we're implicitly tasking our graph model to learn what the role of geometry may have been. And it may be very large, or it may be small. So this is what we're trying to set out to answer. And like I said, the molecular structure, right? It's molecules, because there is Avogadro's number, right? Like 10 to the 20 molecules acting at the same time in a sample. The molecules exist as an ensemble of 3D conformations, right? They're not one structure, they're an ensemble of structures. And the relative proportion of each one of them is related to how low their energy is, right? Through a 19th century distribution. And here, actually, permutations matter, right? For the graph, we want to be permutation invariant, but entropy, if there are many configurations for a molecule with entropy, with different atomic arrangements, then that counts for entropy and stabilizes, counts as a driving force. Like I said, the most stable, right? In this case, it will be, maybe this little blue well might not be the one that is actually biologically active. So our way to think about 3D should, in principle, be able to realize that there are multiple wells of energy and multiple local configurations that are local optima, right? So the molecule will exist like this for a little while. and then eventually go hop and become something, some other arrangement in some other well. Like Gian said, right, like the ground truth of the 3D is not available. The crystal structure from databases is definitely true, but it's also in a solid and just one conformation. It's not the ensemble of conformers the molecule could exist as. So even if it's a very refined and excellent ground truth, it's not the whole thing that's going on in solution. So we do lots of simulations, and simulations are a good trade-off between cost and ability to identify these conformers. So what did we set out to do here? So we set out to try to answer two sets of questions. One is related to drug repurposing and COVID, thanks to the excellent, community building efforts from speakers here and the organizers. We all have the same data sets to play with, and we also have sort of the same tasks to compare. So we're testing our 3D hypothesis on the repurposing of knowledge from SARS-CoV to SARS-CoV-2, right? So we want to repurpose known drugs that bind the 3CL protease in the COVID virus, in SARS-CoV-2. And for that, we're going to pre-train models on a very analogous protein from the SARS-CoV-1 virus, for which there was a very large screen in 2010. But also, in addition to sort of seeing how well we can do this task, we want to gain deeper insight into, okay, well, 3D is biologically very relevant. Are our graph models learning it and inferring it? Are our graph models completely unaware? So can we enhance our graph models with 3D information such that we make up for what they may not be seeing? And we also set out to create this hopefully gold standard data set of conformations so that people can, like Gian, do the amazing work like that. And for that, we used a simulation approach that is called metadynamics. And what it does is, starts at the bottom of a well, starts in a basin, and it starts twisting and moving around the molecule such that it never visits the same spot again. So it starts adding energy to the simulation so that the molecule wiggles away from wherever it is and explores as much phase space as possible. And it, keep track of all the local minima it's visited on the way. For this, we use quantum mechanics, and this is something very important. If you go and look at Gian's paper, it's pretty subtle, but I'm sure some people in our community might see that the nitro groups are pyramidal, because the force field that is working behind the scenes doesn't know that should be a flat structure, but DFT is one of the tools that is aware of that and will give you flat sp2 groups in the nitro. So with a lot of support from NASA and this EXCEED call for COVID computation, we annotated a big data set of molecular structures. We did two things. We did the SARS-CoV-1 plus every approved or sort of repurposable drug we could find. So there's going to be, in addition to the training data for SARS, a little extra data. And of course, people are welcome to use these 3D geometries for their tasks. This includes, like I said, the broad repurposing set. We just learned about the refactor, which we're going to execute in the next couple of days. And we also annotated the sort of this standard QM9 data set that contains really ugly and nonsensical molecules, but it's exhaustive up to 9 atoms. So it very densely covers a region of chemical space that is a little bit weird, but it's definitely a baseline for everybody in this community. Okay, so now we've got, there is, some numbers here, right? So molecules on average have, tens of atoms, so they're pretty large, right? They're drugs, and they typically have of the order of tens to thousands of different conformations, right? So the most flexible ones will have thousands of conformations, and some of them will be extremely rigid and have just a few. And we also know, which could help folks like Gian to drive their models, the energy of each configuration, right? We know the energy of the conformations, and that's the relative probabilities, which one could use the flow model to not just speed out structures, but speed them out in proportion to the relative energy, such that it follows, the Maxwell-Boltzmann distribution, like Monte Carlo would. in terms of our property prediction task. So what are we going to do? How do we ask the question of what 3D does in this context? Where we're going to start with a graph, and we're also going to start with all the conformers that we found for it. And then we're going to do what the community has agreed is a very strong baseline, which is use the Chemprop architecture and approach. So we're going to use the Chemprop repo, right, and predict a embedding. Now, alongside this one copy of the graph, we have n copy of the conformers. So we're going to pass for each conformer, we're going to annotate the bonds that Chemprop uses with extra features. And we're also going to make these distance bonds, let's call them, reach out a little bit farther. And this relates to some of the questions we had earlier before. So instead of having, every atom sees every other atom up to distance 5, right? And these edges are annotated on with a projection of the distance onto a Gaussian basis, like they do in Schnet. This comes from Schutte, the first author. So it's a pun on the first author's name. This is a very, very effective 3D learning architecture that has been, for the physical simulation communities, is definitely the state of the art. It is invariant to rotation because it uses the distance, the pairwise distance between atoms. So it's invariant to rotation, which is vital for energy conservation, right? The energy of your system shouldn't care about the rotation. Some modern architectures are now equivariant and do a little bit better, but the memory costs scale. So we settled for Schnet to add, like I said, these extra edge features on top of the Chemprop features. Now we do message passing, right? The bonds that are far away only exchange where they're mid away, right? They're not covalently connected, but nearby exchange just Schnet messages, and the bonds that are covalently connected exchange Chemprop and Schnet messages. And this gives us one embedding for one conformer. And now we do this for up to, if a molecule has more than 100, we only put 100. That's already a lot of memory. And if a molecule has less than 100, we use however many it has. We add another vector, which is just a projected version of the probability, right? So we make the neural network aware of the relative probability of encountering this conformer. So, this is information that will be there and it might be used. Again, we mix these two in a learnable fashion. We end up with one final fingerprint or embedding for every conformer. And then we pull all the conformers together with one attention head. So we also added attention so that every conformer can attend on the other conformers and make a final fingerprint. So this is a much, much bigger model than Chemprop. It has a lot more inputs and it requires a lot more memory. And now we set up to see sort of how it does for these tasks. And to remind you, right, this was an experimental screening of molecules that bind a protein, a purified version of a protein. So this is a very 3D task, right? And this is more 3D, right? Because the action that is happening is binding. It's not biological activity in a broad sense, but it's a very, intermediate assay of just protein molecule interaction. So this should be a good metric of the strength of 3D. So we trained on this about 300,000, right? 60-20-20 splits. This is the mean of 10 models. So for every number, this will be that we present, every performance, this will be the mean of 10 models, which typically agree to the last digit that we're showing. So we've got reasonably good statistics, and every model was hyperparameter optimized independently to find the best performance that we could. So what do we find, right? This is our pure graph approach for precision recall, and this is once we add 3D information. So it's a big boost. I mean, the value is low to start with because there is, hundreds of positive values, positive data points in hundreds of thousands of training. So it's very, it's very imbalanced. But we see a boost from the 3D. And interestingly, and this is the part where the ablation studies are a little bit harder to interpret. It's not exactly clear what part of the 3D information is bringing the full value, right? So this is using attention up to 100 conformers, and we expose the probabilities, right? Here, we didn't let the neural network learn the relative weights. We just forced to be the fingerprint be a Boltzmann weighted sum of the individual fingerprints. And you can see it's hard to see what exactly is driving. A single conformer was actually the champion. So just showing one single conformer actually almost performs as well as showing 100 conformers. And in terms of ROC, we see similar behavior to some degree, which is a little bit of a boost from 3D, and in this case, equal weights for all the conformers helps. This is for the big data approach, where one could suspect or expect for graph convolutions to do very well, because over 300,000 data points, there is enough representation learning driving force. Now, for transfer learning, we're going to call MPNN a de novo graph model that we fit just on the little data that we have for transfer learning as a baseline. And then this is the naive, just taking the embeddings out of Chemprop, of our 2D version of Chemprop, and predicting properties. So this is worse than starting from the beginning. It's one of those places where transfer learning doesn't quite work independently. Of course, Wen-Gong has this great domain adaptation paper where they got this to work much, much better than the naive baseline. And you can see again that the 3D boost helps a little bit, and it helps more than starting from zero, which is something that the graph itself wasn't doing, both for PRC and for ROC. So in summary, we have what we hope is a gold standard data set for conformations to work on comparisons of 2D versus 3D representations, like we do, to create 3D geometries. And also the 3D geometries are out there for anybody that needs them, compared with graphs, and concluded that at least for this task, there is a little boost from 3D, but I think it's open to, for us and for the community to figure out, are we extracting the most of this 3D in this way? Are there other better approaches, right? There was this molecular attention transformer paper that used 3D. So what is the best way to tease out 3D information now that we have it? And just while we set up for the questions, thanks Simon, who's been the guy driving this work. Thank you.
Thank you very much, Rafa. Time for a single question. You have just one question from Joshua Bencher. Do you take into account the relative frequency of different conformants when you aggregate their representation? Rafa, maximum a minute. Go ahead.
Yeah. Like I said, yes, we do. We expose them, so we know the relative population through Maxwell-Boltzmann statistics and the entropy. So we know exactly how often they appear. We make a feature for that. That was, I think, the pink feature or the yellow feature next to the red. I can share, but yes, it goes in. But you saw sometimes the neural network uses it, sometimes it doesn't.
Thank you very much, Rafa. Great talk.